Welcome to the multivariable calculus section. In this section, we'll be discussing double integrals in polar coordinates. So now that we discussed double integrals over a general region or over rectangles, there is a key word being over. So in this section, we're still going to be dealing with double integrals over a general region. However, we're going to be discussing them in polar coordinates. So recall from the parametrics and polar coordinates unit that we have the following substitutions. We know that x is equal to r cosine theta, y is equal to r sine theta, and r squared is equal to x squared plus y squared. So previously we indicated that the double integral over the general region D of f of x, y, dA is actually equal to BA and G2x, G1x, f of xy, dy dx. So we know that this is our equation, however this is regarding only rectangular coordinates. So here we have an illustration of what this actually means in rectangular coordinates in polar coordinates. So initially we were dealing with something that looked like the following. So if we had a point in space, we know that that point would have an x and a y. However, in rectangular coordinates, we know that is a slightly different case. So in the event that we were to have a function, and that function would lie something like the following. We can say that this would be representative of, oops, let me get a brush. This curve would be representative of R2H. R2 is equal to H2 theta. And we can say, let's make a different color. This function is representative of R1, which is equal to H1 theta. Now, we can also draw another line and indicate that this is how far our theta gap opens. And now using this, we can interpret this idea in polar coordinates. So essentially what we're saying is that D is equal to the region r cosine theta, which is in prior x. And let me remove that theta. Our cosine theta, which is our x, and our y, obviously, our sine theta. And then it is bound by alpha, which is less than and equal to our theta, which is less than or equal to beta. And h1 theta is bound by our r, h2 theta. And essentially that would be our domain. So this means that instead of writing it as the following, we're going to actually change this to look something along the lines of the following. We can say that the integral over the general region is no longer going to be of f of xy, but it's going to be from beta to alpha. And we're going to say from h1 theta, because it lies, to h2 theta. Or these are vice versa, with depending on whatever is going to be on the top. So in the event that we had a function where h2 theta lies on the top, then we would say, okay, h2 theta is here, or in our case, we're saying that h1 theta is going to lie here, and h2 theta will lie here. And that means that the function r cosine theta, r sine theta, is bound with respect to r dr d theta. Now this r is very important to note because a lot of students forget that this r is there, and when they put their function in polar coordinates, they don't multiply their function by that r. So it's important to note. So say if we had our function is equal to r squared cosine theta plus r sine theta. Well, when we compute this integral, we should say that we're integrating r cubed cosine theta plus r squared sine theta. So that's just a little insight on double integrals in polar coordinates. If you need additional assistance, there's a bunch on the website, and if you want to try out more practice problems, the website has that as well. Thank you.